To simplify higher root radicals with variables, the process is very similar to simplifying the square roots with variables. The only difference now is that the index number is not 2. It's going to be higher, so it can be 3, 4, 5, or 6 continuous. So let's look at our first problem. Our index number is 4. So therefore, to break down the fourth root of 2,592, I need some of the perfect fourth root numbers. And to get those numbers, I will just list a couple of them here. So for example, 2 to the fourth power is going to be 16. So therefore, fourth root of 16 will be 2. 3 to the fourth power is 81. And then 4 to the fourth power is 256. And you can continue the list here. So I know that 16 can go into 2,592 162 times. So now I'm going to take the fourth root of each number. And we know fourth root of 16 is going to be 2. And I can break down 162 even more by 81 because 81 times 2 is 162. So again, take the fourth root of 81, which is 3. And I can't break down 2 anymore, so that's it. So now take the numbers outside the fourth root and multiply them. 2 times 3 is 6. And I'm going to leave some room for the variables. And we have fourth root of 2. Bring down the 2. And for the variables, all you have to do is take the exponent for x, which is 25, and then divide it by 4. So basically, how many 4s can go into 25 maximum? Well, we know that that's going to be 6 because 4 times 6 is 24, but there's still 1 remaining to make it 25. So there must be 1x remains inside the fourth root. And then for the y, how many 4s can go into 30 maximum? Well, that would be 7 because 4 times 7 is 28 and there's still 2 remaining. So therefore, there must be 2 y's inside. And whenever you do square root, fourth root, or sixth root, basically taking an even root, your answer must be positive. Okay, so therefore, when you have a variable with an odd exponent, which could give you a negative result, make sure you put absolute value around that variable. So in our case, we only have to put it around the y. And that's the simplified version for this problem. And now let's look at next one where the index number is 5. So the odd root can have a negative solution. So therefore, at the end, you don't have to worry about adding the absolute value sign. So because fifth root or cube root or seventh root of a negative number is always going to give you a negative solution. So you might as well just go ahead and put negative in front of the fifth root. And now the rest of it will be exactly the same thing you did earlier. And the only thing is that this time I need some of the perfect fifth root numbers. So I'm going to list a couple of them here. So 2 to the fifth power is going to be 32. So therefore, fifth root of 32 is 2. So 3 to the fifth power will be 243. And the 4 to the fifth power is 1024. So 1024 can go into 8,192 8 times. And now I can take the fifth root of each number. So we know what fifth root of 1024 is. That will be 4. And then that's it. I can't break down 8 anymore. So again, take the numbers outside the fifth root. And so don't forget the negative sign. So we have negative 4. Leave some room for the variables. And then fifth root of 8. And for the variables, just like what we did earlier, take the exponent inside divided by the index number, which is 5. So how many 5s can go to 13 maximum? Well, that would be 2. So therefore, it's m squared. And 2 times 5 is 10. So there's still 3 remaining, so you have m to the third power here. And for the n squared, because 5 cannot go into 2, so n squared remains inside the fifth root. And then for p, the exponent is 32. So 5 can go to 32 6 times maximum because 5 times 6 is 30, and there's still 2 remaining. So therefore, it's p squared inside.